Hello everyone, wishing you all a very good evening. I am Khushboo, and that's true, I have traveled over 7,000 kilometers from India to be here today at PHP Day. It's my first time in PHP Day and in Verona, and I'm having a great day so far. Today, I'm going to talk about Async PHP with coroutines, but before that, I'll just give a brief introduction about myself. So I'm Khushboo. I currently work as a platform engineer at Appwrite. Appwrite is an open source backend as a service. It has our GitHub repository is around 48,000 GitHub stars, and it is a PHP core backend product. And basically, we help developers build websites easily, build their backend easily. And so today this talk is about PHP and my experience with it, my experience at the company. So Appwrite as a product, it started as an open source product which was self-hosted. When we saw increasing demand, we decided to launch a cloud offering. And as the scale grew, obviously the product ran into scalability challenges, and coroutines was one way in which we enhanced the performance of the system. And today I'm just going to share a few bits about it. So we all know that PHP has traditionally been a language that everyone loves to criticize about concurrency limitations. But today I'll show you how modern PHP breaks these constraints. And by the end of this talk, you'll understand how PHP coroutines work and when they are the right solution. Obviously, just like any other solution, there's no perfect solution. Each solution has its pros and cons. And today we'll discover how PHP evolved into what it is today. So before talking about coroutines, let's talk about the traditional PHP bottleneck. We all know that PHP was originally designed as a template language for web, and its execution model reflects its origin. So let's talk about how basic request response cycle works in PHP. So obviously, the client makes a request. A user's browser sends an HTTP request to a web server like Apache or Nginx, and then the web server handles the initial request. It knows that it is for a PHP file. So the PHP process initialization happens. So the server can either spawn a new PHP process if it is running in the CGI mode, or it can pass the request to a PHP FPM worker process, or it can pass the request to mod PHP if using Apache with the PHP module. In any of these ways, the execution would be completed by loading the script, executing it from start to finish, generating the output, and sending it across. The response would be received by the web server. It will transfer it to the client. And after that, the process termination would happen if using the CGI mode, or the worker would become available to another request if we are using PHP FPM. So the problem is that there are certain challenges with synchronous PHP. First of all, the architecture was simple, designed for synchronous request response. However, like we know that for PHP, traditional PHP, it had the one request, one process model. So we all have studied operating systems as engineers. We understand that processes have their own memory space. They require memory for the PHP runtime environment. And even with the PHP FPM pools, where there are multiple requests like process pools, that also has problems with concurrent users. So if you have 10 concurrent users, you would need 10 PHP processes. If you have 100 concurrent users, you will need 100 PHP processes. That's quite a bottleneck. Not just that, it also has blocking I/O. So if your application is I/O intensive, in that case, the operations are gonna wait for I/O. Basically, if it is database queries, API calls, or file operations, it blocks the entire process until the response is received from the I/O. Right? So for example, if I had to do something like PHP get file contents from a URL, my PHP process is gonna wait and do nothing until the I/O operation is complete. It is a waste of resources. So let's look at a simple example. In this case, let's say that there was an e-commerce platform. It had to make 3 API requests, one for getting the products, one for getting the prices, and one for reviews. So it would actually do it synchronously, and it would wait for all the 3 requests to finish, and the total time would be the addition of all the 3 requests. Right? And if there are multiple users, the performance becomes even worse. So there are obviously scaling challenges. There is resource consumption, that each PHP process has its own memory. It loads extensions, application code, and each web server has a certain connection limit, and they can only maintain certain number of PHP processes. There is context switching happening between different processes. and I/O inefficiency because we are just waiting for I/O operations. So the PHP community didn't just sit idle waiting for coroutines. The limits of synchronous model were pushed in multiple ways. As discussed, PHP FPM process rules was one way. So it can either be like pre-spawning of multiple worker threads and reusing them for multiple requests, or these can also be spawned on demand and then used based on different requests. Also, there is a way to set the maximum number of requests, after which the worker threads are recycled, right? So while PHP FPM processes had better concurrency, but each worker still required, requests synchronously, and it would leave the I/O wait time again as a fundamental bottleneck. The other option, as we discussed even earlier in the talks today, opcache also has JIT compilation in PHP 8.0 onwards, which started improving PHP's execution model a bit. There was also preloading, which was introduced in PHP 7.4, which kept frequently used classes in memory between the requests. And obviously, if you are using databases like Postgres, there are tools like PG Bouncer or Proxy SQL to maintain database connection pools, which overall makes the request faster. So these solutions significantly improved PHP's performance, but still there was this fundamental problem that there was one process per request. So why is there a need of asynchronous PHP? If there is synchronous PHP, requests take time to happen. Each request happens one by one, but we need ways to make it happen parallelly. So around 2012 to 2013, inspired by Node.js's success, libraries like React PHP emerged, which introduced event-driven programming to PHP. So there was event loop. I would like to show some code here. Let's zoom in. So this code is written in React PHP form. So let's say that there were multiple API requests that we had to make. So these are just placeholders. Can everyone see the code from behind, or should I zoom in more? Just give me a thumbs up if it is visible. Perfect. So let's look at this particular method first. So it's a simple thing. It's just iterating over the URLs. It is printing the start time for me. It is then basically it's inspired by callbacks in JavaScript. So there is a success callback and an error callback. So if it just tries to get the body from the URL, if it is able to, it's just gonna print completed request. It's gonna increment the number of completed requests. And if it fails, it's just gonna report the error. And this is the method which is just checking if all the requests are complete. If all are complete, it's just gonna print the time. So I'm just gonna run it here, and I would like you to notice what's happening in the browser, in the terminal. So it's gonna make these requests at the same time. It's not gonna wait for requests to wait for each other. And after it has completed, it has printed the output of each API request. Also, so notice here that it made 3 API calls at the same time. Then it waited for all of those responses to compile. And if you notice, the order of the calls in the output is different as compared to the order in which they were called, which means that they were actually called in parallel. And as we can see, it was executed in 5 seconds. So this actually solves the problem of running requests in an async fashion. But again, it is, first of all, it has its own challenges. First of all, it is using event loop kind of a thing, which is not very intuitive for PHP developers. And just like with any callback approach, there can be solutions like situations where you get into a callback hell, where one callback is called recursively from another, and so on and so forth. And the code can become easily unmanageable and really huge. Obviously, to tackle this, another approaches like promise-based approaches were introduced. But again, not like they were again great. They improved performance by a lot. But could we do better? So there were some key drawbacks in these early async approaches. The first one is the cognitive overhead. So as discussed, PHP is not meant to, very intuitively work in the way that JavaScript works in an event loop fashion. So it was a complex mental model for developers. It was a different style of programming. Then error handling also became a little complex because the stacks kept on growing. It was really hard to debug what's happening in the code. And also, ecosystem compatibility became a challenge because most PHP libraries aren't designed to be async, and it required special async variables for database drivers, etc. And the code readability also became hard in the callback approaches where there were multiple callbacks within each other. So PHP in 8.1 introduced something called as native fibers. So what are PHP fibers? These are lightweight, cooperative concurrency enablers. Basically what happens is that it is inherent to PHP. You don't need to install any library to use it. You can actually manually control the execution in a thread. So for example, if you do suspend, it's going to pause the execution. You can do something else in the meantime. And when you do resume, it's going to start again. So it improves the async workflow with reusable code. And there are different use cases for it. So async I/O operations are now possible inherently in PHP. Task scheduling is pretty easy. And the coroutine-based servers and libraries can also use it. But it's important to know that these fibers are not exactly OS level threads. There's not exactly true parallelism. It's not multiple things happening in parallel, but it's like one thread which is pausing in between, picking up something else, again resuming the operation. So great. It's really nice to have something like this in PHP. And we can actually also take a look at the code example. So I have the fiber code here just for reference. So it's a very simple example here. So I'm just creating a new fiber. I'm printing the fiber started. After this, I'm suspending it, right? As soon as I suspended, the flow would actually go here. So look at line number 17 here. I am printing starting fiber. I call start, right? After this, I enter here. And here, after printing fiber started, I'm suspending it, and I'm passing a message to it. So if I hover over suspend, we can know that it is actually taking a value. And as I suspended, the flow is again going to come out, right? And again, after this, I can resume this fiber. So I can use fiber resume. And I can again, resume and suspend multiple times. So basically, you can actually control the flow of what's happening. At any time, if you want, you can pause it, you can resume it, and you can do other things in the meantime. So this is great. But then another thing that is actually useful that we also use in Appwrite is Swoole. How many of you have used Swoole? Okay, very few people. So Swoole is actually a very powerful and comprehensive approach to async programming in PHP. It is actually a C-based PHP extension which changes how PHP applications handle concurrency and I/O operations. So Swoole operates on a little different model than traditional PHP. It's an event-driven programming model. So it implements high-performance event loop in C. It also has a persistent process pool. So basically, the application stays in memory, and between the requests, it eliminates PHP's traditional bootstrap overhead. It also has native coroutines, which we are going to see in a bit. It has these coroutine support without handling any callbacks. And it also has integrated components, which means that it has built-in TCP UDP servers. You have your HTTP WebSocket servers, task workers, etc. And the process model looks like this. It has multiple processes. So the master process is they're responsible for accepting new connections and distributing them across workers. The manager processes take care of, look at the worker processes and restart them if required. And the worker processes handle the client connections. So what are exactly Swoole coroutines? So Swoole coroutines are basically lightweight user-level threads. Right? They are not actual threads. They're, again, very lightweight user-level threads which enable async, non-blocking I/O operations within a single process. And they allow your PHP code to perform other tasks while it is waiting for I/O operations. And how it works is that you do not have to do it manually like PHP fibers. Swoole's coroutine scheduler automatically knows that when it has to switch the context between coroutines based on the I/O status. So if an operation is waiting for I/O, it's going to know when it has to switch context. And the coroutine hooks allow you to use native PHP coroutine context without blocking the process. So the advantages are that as PHP developers, we still get to write the code in a synchronous looking fashion while it's actually running in an async way. It gives us high performance, good concurrency, and it enables async I/O. So if I just have to give you a quick difference between the native coroutine like PHP fibers that were introduced in 8.1 and Swoole coroutines, the difference is that fibers are native to PHP, whereas Swoole coroutines require you to install the Swoole extension. The concurrency model is that for fibers, you have to actually write the sequence or the logic manually, which means that if you're developing a library of PHP using fibers, then you have to define it in the library itself, whereas Swoole coroutines have this automatic scheduler which knows when to switch context. And uh, like Swoole coroutines are actually easier to use. So if you're just getting started, I think it's easier to implement. It's very high level, whereas I think fibers can be a bit low level. But being low level, they give you higher control, fine-grained control over what you actually want to do. So there are some examples of where you can actually use coroutines. So I think the best use case is when there is a very heavy I/O heavy application. I think coroutines would work really nicely there. Obviously, you can use it when there are heavy database operations, network operations, or task queues. One use case where we used it is log streaming. So when, let's say, a function is building, we also wanted to print logs, which are like live streaming logs. We also wanted to do some audits, etc. So those things needed to happen in parallel. And in those cases, it was immensely useful to us. So now, again, just jumping onto the demo. So I'm just going to show you how we can write Swoole coroutines. Again, since it's a library and extension, I have to import it. And then let's say there are again multiple APIs that I just need to call. So I'm just printing that I am running sequential requests, and I'm capturing my start time. And I'm just making a curl request to these API endpoints, and I am executing it and then closing the connection. And here, this is like a sequential request. Now, how to do this in a coroutine fashion is that I am starting again the time. Then everything that needs to run in a coroutine fashion needs to go inside this co-run function. So it's going to know what all needs to happen in a coroutine fashion. And again, for each API, I'm just doing something in a loop. So every single coroutine goes inside the go function. So here I am making a new client request. I am setting some headers, and I'm just doing client get API URL. And I'm just going to get the ID of it and print it and just close this connection. And again, note down the time here. So let's try to run it and see like what kind of performance difference it gives us as compared to synchronous requests. So this is running sequential requests. It took around 0.6 seconds. And then I slept for 2 seconds. And after that, I ran coroutine-based parallel requests. As you can see, the order of these requests is really different. I don't know if you notice it ran really fast. And here in the performance improvement, we can see it was 8x faster than the synchronous operations. I'm just going to run it once again. So this is sequential. It took 0.2 seconds. After that, it happened in a coroutine-based parallel process. It ran requests parallelly, and again, it was 4x faster. Obviously, it's a much smaller example, so the time difference here is really hard to notice. But when you're actually running it in a production environment, the difference can be enormous. It can be really huge. So that's coroutines. And as we saw some examples of coroutine methods, there are actually a few more. So we saw that the co-run was like a bootstrapped container environment, and it waits for all the coroutines to finish. Then co-go creates and schedules new coroutines. So everything that you want to happen in parallel can go inside a co-go. Then if you want to have a non-blocking sleep, you can use co-sleep. And if you want two coroutines to happen together, you can use co-join uh, for them to wait to each other to finish. And we can also have like much more operations like yield and resume. Now, there's also context, right? Now these things are happening in parallel. What if you want shared context between them? So each Swoole coroutine has its own isolated context, which is its local context. And we can also define some global variables if you want to share some state across multiple coroutines. Basically, each of the coroutines has an isolated environment so that they do not hamper each other's processes or pollute each other's variable pollution. So these global variables are used to share variables. And I'm just going to show you the example of global variables. So As you can see here, initially in the core run, I have first started the core run. Within it, I have defined a global variable, which is like a shared variable. Then inside each go, I am printing the value of global variable to see if they can access it. And within each uh, go, I also have a local variable. So in this one, it is coroutine1 local. And I'm also modifying the value of the global coroutine here. And after this, I'm actually sleeping. The reason is that I did not want the second operation to run first, so I just want them to happen in a synchronous fashion, just to show you that they are actually accessing the global variable and local variables are separated. So this one also has a local variable, and we are just going to print the value. So what's going to happen is that the first coroutine is going to update the value of the global variable, and the second one is just going to access it. So I'm just going to run it here. So as you can see that initially the value of, one second, initially the value of the global variable was shared. Then we came into the first coroutine because the other one is just sleeping for 2 seconds. The value is coroutine1 local. Then it modified the value of the global variable. It is modified by coroutine1, and the local variable is of the local coroutine itself. So this is how you can actually share, different variables across coroutines. But there is also something called as coroutine channels. So you can think of it as inter-coroutine communication again. So it is kind of a queue where different things are added. So it's like a FIFO queue actually. Whatever enters first exits it. So it is a thread-safe and lock-free queue. So channels basically allow you to have inter-coroutine communication, and it can be bounded or unbounded. Again, I just want to show you a quick implementation of the same. So in channels, again, this is how you can initialize a channel. And let's say that I want to download content from Google and Yahoo both, and I just want to know that, when that completed. Let's say I wanted to do a third operation when these two operations complete. How would a coroutine, which is running in parallel, know that the other things are complete? There are so many scenarios in our day-to-day lives where we want things to, rely on one another, or some things to run synchronously while others run in an async fashion. So I'm just going to show you quickly here. So we first created this co-channel. Then inside my go, I'm actually just making a request to yahoo.com. I am just getting the body. And in my channel, I am pushing that Yahoo was done. So it's like a queue. I'm pushing that, OK, my job is done. Then similarly, I'm downloading content from Google, and I'm pushing that Google is done. Now, in my previous example that I showed you, I had added a sleep of 2 seconds because I knew it's just going to take 2 seconds for the local variable or global variables to be modified. But in the case when I do not know, like for what duration I need to wait, I think channels work great. So as you can see, this coroutine is using a channel, and it is just popping from the queue. So it knows that it is waiting for 2 coroutines. So it's just doing a loop of 2, and it is popping. And once it is done, it's going to complete its execution. So just let's quickly run it. So as you can see, it knows that Yahoo was done and Google was done. And this is where it is printing it from, which means that the third coroutine had a context of the other two. Now, let's talk a bit about the performance of coroutines. Obviously, these are just generic numbers. You all can go and try coroutines in your scenarios as well. But on an average, on modest hardwares, with coroutines, you can handle around 10,000 requests per second on a single application server. The memory usage is around 2 MB per 1,000 coroutines, whereas for conventional OS level routines, it is around 2 GB, right? So it's significant difference. And the context switching now just takes microseconds because it is happening very fast in memory. And the latency also reduces by a lot. And there are coroutine compatible I/O operations like HTTP or WebSocket requests. As we discussed initially, TCP, UDP connections are also supported out of box. MySQL and Postgres, Redis, any tools that you use in your everyday life, it is very easy to configure it with coroutines. And socket operations and everything can happen. So that's all from my side. I hope you learned something new today, and it's going to help you in your workflows. Thank you.